Hello everyone, welcome to this tutorial on first and second fundamental forms of a surface. Recall that a space curve is uniquely determined if the curvature and torsion of the curve is known as functions of arc lengths. Similarly, a surface can be unique if two local invariant quantities are known. The two local invariant quantities are called the first and the second fundamental forms of the surface. The first fundamental form is denoted by E, F, and G. The second fundamental form is denoted by L, M, and N. In this tutorial, we are going to define the first fundamental magnitudes and the first fundamental form of a surface, R vector, which is a function of both u and v. We shall also define the second fundamental magnitude and the second fundamental form of a surface, vector r. We shall also establish the expression for the arc length of a curve on a surface, and lastly we shall apply the above in solving problems. To begin with, we look at fundamental form B, point, the surface as an equation vector r and v, which is equals to I f of 1 plus f of 3, where f of 1, f of 2, and f of 3 are functions of both u and v. So the coordinates on P are a function of arc lengths s measured from a fixed point A. So now the derivative of r, since r is a function of both u and v, can be written as dr du plus dr dv, and the change in r with respect to s, that is dr ds, then will be the same as dr du times du ds plus dr dv times dv ds. Let's refer to this equation as equation 1. Here dr ds is a unit tangent. So now let's find the dot product between dr ds and dr ds. By definition, this is the same as the magnitude of dr ds times the magnitude of dr ds times the cosine of theta. Dr ds and dr ds, the angle between these two vectors is 0, and we know that cosine of 0 is 1. And since dr ds is a unit tangent, it means that the modulus of dr ds is 1, and therefore dr ds dot dr ds will be equal to 1. In other words, in terms of magnitude, it means that the square of dr ds is equals to 1. So since r is a function of both u and v, and from equation 1 we had seen that dr ds is same as dr du times du ds plus dr dv times dv ds, then it means that 1 is same as the square of dr du ds plus dr dv ds. So we square whatever is inside the bracket. When we square, we are going to have 1 is same as the square of dr plus twice plus twice dr dv du ds plus the square of dr times v times the square of dv ds. In other words, we can say that 1 is same as the square of partial derivative of r with respect to u times the square of partial u divided by the square of partial s plus twice partial derivative of r with respect to u times partial derivative of r with respect to v times partial v divided by the square of partial s plus partial r partial v times the square of partial v divided by the square of partial s. If you look at the right hand side, in the denominator we have the square of partial s, so we multiply both sides by the square of partial s, then we are going to get the square of partial s is same as partial r partial u dot partial r partial u times the square of du plus twice partial r partial u dot partial r partial v times du dv plus partial r partial v dot partial r partial v times the square of dv. This can be written as the square of partial s is equals to e the square of du plus twice f du dv plus the square of dv times g. In this case, e is same as partial r partial u dot partial r partial u, while f is partial r partial u dot partial r partial v, and g is same as partial r partial v plus partial r partial v. So here e, f and g are called the first fundamental magnitudes of a surface. E, f and g are called the first fundamental magnitudes of a surface, while the square of partial s, which you have said is same as e the square of du plus twice f du dv plus g the square of dv, is the first fundamental form of a surface. So let's consider a numerical example. So we have been given a surface whose equation is vector r is equals to I uv plus j into bracket uv minus v, then plus k into bracket uv minus u. So we are required here to calculate the first quadratic differential form in general, and also specifically we look for it when u is equals to -1 and v is equals to 1. So we are going to look for the values of e, f and g. So we begin by partially differentiate with respect to u. So if you look at the first element here, we have uv. When you partially differentiate the uv with respect to u, we are going to get v. That's why we have I. The second element we have uv minus v. We partially differentiate it with respect to u, we are going to get v. So thus we have plus vj. Then plus, if you look at the last element, we have uv minus u. We partially differentiate with respect to u. Here we are going to get v minus 1 and minus 1 and minus 1 and minus 1 and minus 1, and this is partial r partial u. We now partially differentiate r with respect to v. If you look at the first element, we have uv. When we partially differentiate it with respect to v, you will get u. So we have iu. Then the second element, we have uv minus v. When you differentiate with respect to v, you're going to get u minus 1. Then in the last element, you have u minus u. when you partially differentiate with respect to v, we are going to get 1. That's why you have partial r partial v as iu plus j into bracket u minus 1 plus ku. So we have the partial derivative of r with respect to u, and we also have the partial derivative of r with respect to v. So E we said is partial r partial u dot partial r partial u, and this is same as the dot product between the column vector for partial r partial u and the column vector for partial r partial v. So partial r can be written as v minus 1. So dot the partial r partial v can be written as v minus 1. So we are going to have dot v plus v dot v plus v minus 1 dot v minus 1, and therefore this gives us v squared plus v squared plus the square of v minus 1, which simplifies to 2v squared plus the square of v minus 1, and this is our E. Then next we'll find f, which is partial r partial u dot partial r partial v. So partial r partial u in column form it's written as v minus 1, then dot partial r partial v is same as u minus 1 u. So when we find the dot product, we'll have v times plus v dot u minus 1 plus v minus 1 dot u, and this gives us uv plus uv minus v plus uv minus u, which simplifies to 3uv minus u minus v. Next we look for the value of g, and g is partial r partial v dot partial r partial v. So partial r partial v is same as u minus 1 u, then dot partial r partial v again is u minus 1 u. So we have now u times u, that is u squared, plus u minus 1 times u minus 1 plus u times u, that is u squared, and this simplifies to 2u squared plus the square of u minus 1. So those are the values of E, F and G in general. So those are the first quadratic differential form in general. Then now we specifically look for the values of E, F and G when u is negative 1 and v is 1. So we are going to substitute the value of u with negative 1 and the value of v with positive 1. So in E we now have 2 into bracket 1 squared plus the square of 1 minus 1, and this now simplifies to 2 plus 0, which is equal to 2. Then for f we are going to have 3 into bracket negative 1 into bracket 1 minus into bracket negative 1 minus into bracket 1, and this simplifies to negative 3 plus 1 minus 1, which is negative 3. Then for g we have 2 into bracket the square of negative 1 plus the square of into bracket negative 1 minus 1, and this simplifies to 2 plus the square of negative 2, and that is 2 plus 4, which is giving us 6. And that is the first quadratic differential form when u is negative 1 and v is 1. So now let's look at the arc length. The arc length of a curve of a surface is given by the integral of the square root of e times the square of du dt plus twice f du dt dv dt plus the square of dv dt times g, and we integrate this one with respect to t from the point A to the point B. So we want to prove this one. S is same as the integral of a small change in s from a point A to a point B, and ds can be written as ds dt times dt. Then we integrate this one from the point A to the point B. But ds dt is same as the modulus of dr dt, and therefore s is same as of dr modulus of dr dt. We integrate it with respect to t from a point A to a point B, which can also be written as the integral of the square root of the product between the modulus of dr dt and dr dt, and we integrate it with respect to t from a point A to a point B. And the modulus of dr dt times the modulus of dr dt is the same as the dot product between dr dt and dr dt, because dr dt and dr dt, the angle between them is 0, and we know that the dot product between dr dt and dr dt is same as the modulus of dr dt times the modulus of dr dt times the cosine of the angle, which is 0, and cosine of 0 is 1. That's why the modulus of dr dt times the modulus of dr dt is same as the dot product between dr dt and dr dt, and therefore s is now the integral of the square root of dr dt dot dr dt, and integrate it with respect to t from a point A to a point B. But r is a function of both u and v, and therefore dr dt can be written as dr du dt plus dr dv dt, and therefore s now becomes the integral of the square root of the dot product between dr du dt plus dr dv dt dot dr du dt plus dr dv dt. Then we integrated this one with respect to t from a point A to a point B. So we expand whatever is in the bigger bracket. So this is the integral of the square root of dr du dot dr du times the square of du dt plus twice dr du dot dr dv times du dt dv dt, then plus dr dv dot dr dv times the square of dv dt, and we integrate this one with respect to t from a point A to a point B. And from our previous working, you can see this s can now be written as the integral of the square root of e into bracket the square of du dt plus twice f du dt dv dt plus g the square of dv dt, and we integrate this all with respect to t from a point A to a point B. And therefore we have been able to prove that s is the integral of the square root of e the square of du dt plus twice f du dt dv dt plus g the square of dv dt. So that is the first the arc length of a curve on the surface, where e, f and g are the first fundamental magnitudes of a surface. Let's now consider an example. We look at an example. So find the length of an arc of the curve r, cosine of t I plus exponential of t, the sine of tj plus exponential of t times k, from a point 0 to pi. So t ranges from 0 all the way to pi. So s is the integral of the modulus of and stress 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 and stress. Change in s can be written as the small change in s can be written as ds dt dt. That is, ds dt we integrate it with respect to t, but ds dt we said is same as the modulus of dr dt. That's why we are saying s is the integral of the modulus of dr dt we integrate it with respect to t from a point t is equals to 0 to the point t is equals to pi. So we first of all differentiate r with respect to t, then we find the modulus. So we differentiate the r with respect to t. So for the first element here, we are going to have we treat exponential of t as a constant, and we differentiate cosine of ti. So we are going to have a negative exponential of t, the sine of t. Then we now treat cosine of t to be a constant, and we differentiate exponential of t. So we are going to have exponential of t, the cosine of t. Then this sum we multiply it by I. Then plus the second term is exponential of t, sine of tj. So we are now going to treat exponential of t as a constant, and we differentiate sine of t, and this will give us exponential of t, cosine of t. Then plus we now treat sine of t to be a constant, and we differentiate exponential of t. We are going to have exponential of t, the sine of t. So that sum we multiply by j. And lastly, we have exponential of tk. We differentiate with respect to t. We are going to have exponential of tk. So this is dr dt. Next, we find the modulus of dr dt, and we integrate it with respect to t from 0 to pi. And the modulus is given by the square root of the square of negative exponential of t sine of t plus exponential of t cosine of t. Then plus the square of exponential of t cosine of t plus exponential of t sine of t. Then plus the square of exponential of t. Then that square root we are going to differentiate it to integrate it with respect to t from a point t is equals to 0 to a point t is equals to pi. So when we square, we are going to have exponential of 2t sine of t squared plus exponential of 2t, the square of cosine of t, minus twice exponential of 2t, the sine of t, plus cosine of t. That is from the first square. Then from the second square, we are going to have exponential of 2t, cosine of t, then squared, plus exponential of 2t, the square of sine of t, then plus twice exponential of 2t, the sine of t, cosine of t. Then last square will be exponential of 2t. So everything we put into bracket, you find the square root, and you integrate with respect to t from 0 to pi. So if you look at the first two elements here, exponential of 2t is common, so we can factor it out so that we remain with the square of sine of t plus the square of cosine of t, which we know reduces to 1. Then if you look at the second term here, the third term here, it's negative exponential of 2t, the sine of t, cosine of t. Then if you look at the second last term here, is positive, twice exponential of 2t, the sine of t, the cosine of t. The sum of these two will be equal to 0, because one is negative and the other one is positive. So that the two will cancel out. Then if you look at the fourth term here and the fifth term, also exponential of 2t is common, so we factor out exponential of 2t. So into bracket we have the square of cosine of t plus the square of sine of t, and this is reduces to 1, and therefore here we are going to remain with the exponential of 2t, and then the last term we know is exponential of 2t. So our integral now becomes the integral of the square root of exponential of 2t plus exponential of 2t plus exponential of 2t, which is same as the integral of the square root of thrice exponential of 2t. We integrate from 0 to t from 0 to pi. We can factor out the square root of 3, so that we remain with the integral of exponential of t. We integrate it with respect to t from 0 to pi. So when you integrate exponential of t with respect to t, we'll get exponential of t. Then we apply our limits from 0 to pi, and therefore our s now becomes the square root of 3 exponential of pi minus 1. Let's now look for the second fundamental form of a surface. And the second fundamental form of a surface is obtained as follows. So our surface f1 plus 1 plus 1 plus j of 2 plus kf3, where f1, f2, and f3 are functions of u and v. So we partially differentiate r to get the tangent to u curve on the surface. We partially differentiate r with respect to v to get the tangent to the v curve on the surface. Then we find the cross product between partial u and partial r partial v, and this one will give us the normal to the surface. So the unit normal will be obtained by the normal divided by the modulus of the normal. That is, the unit normal will be partial r partial u cross partial r partial v divided by the modulus of partial r partial u cross partial r partial v. So here, recall that the unit normal, since it involves r in the u and v, so the change in the unit normal, that is dn, can be written as dn du plus dn dv. Also, dr can be written as dr du times du plus dr dv times dv. Now let's take dr times dn. So this will be the same as, from these two, it will be partial r partial u plus partial r partial v dv dot partial n partial u du plus partial n partial v dv. Then if we expand this one, we are going to get partial r partial u dot partial n partial u, then you multiply by the square of du, then plus partial r partial u dot partial n partial v multiplied by du dv, then plus partial r partial v dot partial n partial u times du dv, then plus partial r partial v dot partial n partial v, you multiply by the square of dv. This can be written as L, the square of du, plus twice m du dv plus n, the square of dv, where L in this case is partial r partial u dot partial n partial u, while m is same as partial r partial u dot partial n partial v plus partial r partial v dot partial n partial u, and n is same as partial r partial v dot partial n partial v. So this quantity second, which is equals to L, the square of du, plus twice m du dv plus n, the square of dv, is referred as the second fundamental form of a surface, where L, m, and n, we refer them as the second fundamental coefficients of a surface. We can have another form of the second fundamental form, whereby we know that dr du is the tangent, and n bar lowercase is the unit normal. The unit normal n dot dr du is equals to 0, because the angle between the two vectors is 0. Sorry, is 90, because they are perpendicular, and cosine of 90 is 0. Similarly, n dot dr dv will also be 0, because the angle between n vector and dr dv vector is also 90, and cosine of 90 is 0. Here, L will now be the same as n dot the second partial derivative of r with respect to u. M will be the same as n dot the second partial derivative of r with respect to both u and v, and n will be the same as n dot the second partial derivative of r with respect to v. We'll now consider a numerical example. So in this example, you are told that the surface ui plus vj plus k into v squared. So we partially differentiate to u. So when you differentiate ui with respect to u, you'll get 1, so that's why we have I. When you differentiate v with respect to u, you'll get 0, that's why we have 0j. When you differentiate u squared minus v squared with respect to u, we are going to get 2u, that's why you have 2uk. So partial r partial u will be I plus 2uk. Then we partially differentiate again with respect to u. So in the first element here, you can see we have 1i. When you differentiate it again with respect to u, you'll get 0i, and therefore it will be 0. Then the second element, these all respect to u, will get 2k. Therefore the second derivative of r with respect to u will be equal to 2k. Then partial r partial u, we have obtained it to be I plus 2uk. We partially differentiate it with respect to v. In the first element we have 1i. When we partially differentiate it with respect to v, we'll get 0. The second element we have 2uk. When we partially differentiate it with respect to v, we'll get 0. And therefore it means that the second derivative of r with respect to both u and v will be equal to 0. So back to r, we now differentiate r with respect to v. In the first element we have ui. When you differentiate it with respect to v, you'll get 0i, which is 0. The second element we have vj. When you partially differentiate it with respect to v, you'll get 1j. That's why we have j here. Then in the last term here, we are u squared minus v squared. When you differentiate it with respect to v, you'll get negative 2vk. Therefore partial r partial v will be equal to j minus 2vk. Then we partially differentiate these with respect to v again. So the first element is j, that is 1j. When we partially differentiate with respect to v, we'll get 0. The second element we have negative 2vk. When we partially differentiate it with respect to v, we'll get negative 2. And therefore the second derivative of r with respect to v will be negative. So we will find the unit normal, and we say that the unit normal is same as the normal, which is partial r partial u cross partial r partial v, divided by the modulus partial r partial r partial r partial v. So we find the cross product between partial r partial u and partial r v, and this will be the same as I plus 2uk cross j to vk. I plus 2uk can be written as I plus 0j plus while j the second one here can be written as 0i plus j minus 2vk, and therefore the cross product can be written as the modulus of ijk 1 0 2u 0 1 negative 2v be expanded to, so we'll have I into bracket 0 times negative minus 1 times 2u, then minus j into bracket 1 times negative 2v minus 0 times 2u, then lastly plus k into 1 times 1 minus 0 times 0. And partial r partial u cross partial r partial v simplifies to negative 2ui plus 2vj plus k. Then now we find the modulus of this, and the modulus will be the square root of negative 2u squared plus 2v squared plus 1 squared, and this simplifies to the square root of 4u squared plus 4v squared plus 1. So remember, our aim was to get the normal, and we said the normal will be this the unit normal, and we said the unit normal will be the same as the normal, which you have obtained it to be negative 2ui plus 2vj plus k divided by the modulus, which we have is the same as the square root of 4u squared plus 4v squared plus 1, and therefore the unit normal lowercase n will now be equal to negative 2ui plus 2vj plus k divided by the square root of 4u squared plus 4v squared plus 1. Now we look for the second fundamental coefficients. So we begin with L, which is obtained by n dot partial the second derivative of r with respect to u, and we have seen that the second derivative of r with respect to u is given by 2k, and therefore we'll take the unit normal dot 2k, and this is what you are going to get. And you can see here 2k can be written as 0i plus 0j plus 2k. So when we find the dot product between this and this one here, we'll just have k dot 2k, and k dot k is 1, and therefore L will be 2 over the square root of 4u squared plus 4v squared plus 1. Then next we look for m. M is the dot product between n and the second derivative of r with respect to both u and v. We had seen of r with respect to both u and v to be equal to 0, and therefore it will be the unit normal dot 0, and therefore it means that our m will now be equal to 0. Then lastly we find capital N, which is same as unit normal n dot partial derivative of r with respect to v, and we had seen that the second with of r with respect to v to be equal to negative 2k. So we'll take the unit normal dot 2k and dot negative 2k, and negative 2k can also be written as 0i plus 0j minus 2k. So when we find the dot product between this and this one here, we are going to only have k dot negative 2k. K dot k is 1, so you'll have 1 times negative 2, which is negative 2, and therefore n is negative 2 over the square root of 4u squared plus 4v squared plus 1, and this gives us n, and therefore we have been able to obtain the second fundamental coefficients L, m, and n, and therefore the second fundamental form will be given by the square root of L, the square of du plus twice m d plus a plus n, the square of dv. When we substitute the value of L, m, and n, then from equation 1, 2, and 3 above here, this is equation 1 for L, this is equation 2 for m, and this is equation 3 for capital N. Then it is simplifies to, you can see the common denominator there is the square root of 4u squared plus 4v squared plus 1, and therefore we are going to have twice the square of du plus 0 du dv minus twice the square of dv, which simplifies to twice the square of du minus twice the square of dv divided by the square root of 4u squared plus 4v squared plus 1, which gives us the second fundamental form of that surface. And that marks the end of this tutorial. So in this tutorial, I've been able to achieve our objectives, which was to define the first fundamental magnitude and the first fundamental form of a surface. We have also been able to define the second fundamental magnitude and the second fundamental forms of a surface. We have also established expressions for the arc length of a curve on a surface, and we have also applied above the problems. Thank you for your participation. May God bless you.